So it's like last time, I'll just go 1 or 2 minutes to let the
Yes, please.
people join.
Of course.
Okay, I think we're good. Let's get started. So welcome everyone. Thank you for joining us for this second lecture in the lecture series on level set methods for structural topology optimization. And just like last time, we have Professor Grégoire Allaire, who will be presenting together with Charles Dapogny, and they will be tag teaming this presentation here today. And then with that, go ahead, please, Grégoire.
Good afternoon, everybody. So this is the second part of our webinar on the level set method. And today we are going to discuss some details about the computation of shape derivatives, and then give also many advanced algorithm or part of algorithm for the level set method that were not discussed during the first part of the webinar. And then, of course, show further numerical experiments. So let me remind you what we discussed during the first webinar. So the level set method consider a shape and topology optimization problem where the variable of optimization omega is a domain in RD, d equal 2 or 3 in general. We compute derivative by using the notion of Hadamard boundary variation. That means that variation of original shape omega is parameterized by a vector field theta, meaning that every point x in the domain or its boundary is moved to a new location x plus theta of x, so theta is like a displacement field. And then we compute the shape derivative by just performing a Taylor expansion in terms of theta being small. And then this is coupled with a second very important tool, which is indeed the notion of level set introduced by Osher and Sitian, which represent a domain omega as a negative part of a function phi defined on Rd with value in R. Good. So then at each iteration of an optimization algorithm, a shape omega n is represented by a level set function in a fixed mesh. Typically, during the first webinar, we were discussing a Cartesian mesh T of the domain, computational domain capital D. Here you have a picture which is an example of this. And then the shape omega n is represented by the discretization of this level set function on the vertices of your mesh T. So shape is not exactly mesh. And one thing that we maybe forgot to discuss during the first webinar was that the void or the holes in the domain are represented with an ersatz material, so a very soft material which which is placed, if you prefer, inside the holes. Then once we have computed the shape derivative, from this we deduce a descent direction, a velocity, theta n, which is used in a level set equation to update in a level set algorithm to update the level set function. Good. So a typical algorithm will be to initialize with some given fixed mesh of your computational domain D. You initialize a level set function phi 0 for representing the initial shape. And then at each iteration n, you solve the state on the adjoint equation with this ersatz material inside the holes. You identify the descent direction with these vector fields Vn, which is typically in the direction of the normal from the formula of the shape derivative. Then you solve the level set Hamilton-Jacobi equation, which allows you to advect the previous level set phi n to define a new level set phi n plus 1. That defines your new shape omega n plus 1. You insert a stopping criterion, typically some measure of the norm of the velocity field. If it is small enough, we stop. And then at the end, you get the level set function of the optimized shape omega star. Good. So the presentation today is divided in 4 parts, and the first part is devoted to calculation of shape derivatives. So here is again the picture of how, starting from a given shape omega, we do variation according to a vector field theta. And the definition of the shape derivative is that you perform a first order Taylor expansion when theta is small, and the first order variation here, j prime of omega of theta, is exactly the definition of the first order derivative of the shape derivative. So during the first webinar, we've seen 2 very simple objective functions, and actually this is only 2 examples that you need to remember. From this, you can compute almost all other shape derivative. So first, if j of omega is simply the integral on the domain omega of a fixed given function f of x, then the shape derivative in the direction of a vector field theta is simply the integral on the boundary of the same function f times a normal component of the vector field theta. The second example is now a boundary integral on the boundary of omega of again a fixed smooth function j, and then the shape derivative in the direction of theta is simply again the integral on the boundary of omega of the normal derivative of g plus the mean curvature kappa times g, again multiplied by the normal component of the vector field theta. Now I'm going to explain that if we now differentiate a much more complicated objective function, this will be thanks to the method of CR that I'm going to explain. The same type of difficulty, and you only need to know the 2 previous examples to compute almost all possible shape derivatives. So before that, let me very briefly review the adjoint method, the very classical adjoint method. It should be known, I guess, from most people who are performing structural optimization. And of course, one of the original reference is a book by Lyons in the 70s, but you have very nice, comprehensive and application-oriented introduction in those 3 references that you will find at the end of the slides. So in general, if you do optimization with a model. Let me simply describe it in a very simple setting. Let's say a vector valued setting. The optimization variable is rho. Think about the density, but the objective function not only depends on rho, but it depends also on the solution of a state equation u index rho. And let me simply, after discretization, write the state equation as a linear system where you have a matrix A, depending on rho, your design parameter, density if you want, times a vector u rho equal to some vector of forces, right hand side B, which is again a vector. Okay, and so this is a very simple setting that could be obtained after discretization of many possible design problems. Good. And then I'm going to explain the adjoint method, which is a systematic way to compute the derivative of this objective function. So the idea is it's a optimization problem with a constraint, which is a state equation. So in such a setting, it's customary to introduce a Lagrangian. And the Lagrangian is simply the sum of the objective function plus the constraint multiplied by a Lagrange multiplier. So actually the adjoint vector P is interpreted here simply as a Lagrange multiplier for the constraint A, depending on rho, multiplied by U equal to B. Okay, so you write the sum of the objective function plus the constraint times P. And then it's well known that, of course, if you differentiate the Lagrangian with respect to P, you get simply A times U minus B. And then if you equate this partial derivative dl over dp equal to 0, you get the state equation. And then similarly, the definition of the adjoint state is that this is a partial derivative of L with respect to U equal to 0. That gives you the adjoint state, which is simply the matrix A transpose times P equal to minus dj over du. That's a definition of the adjoint state. And then the classical theorem is that actually the derivative of your objective function is simply the partial derivative of the Lagrangian with respect to rho. And if you make this computation explicitly, this is dj over d rho. Of course, the objective function depends on rho, but it also depends on u rho. And so you have this additional term that comes from the partial derivative of the Lagrangian, which is p, the adjoint, scalar product with A prime, the derivative of the matrix with respect to rho, times U of rho. Okay? And the proof of this theorem is very simple. It simply amounts to replace any vector u by the precise vector u rho solution of the state equation in the Lagrangian. And of course, because the constraint is satisfied, this Lagrangian reduces to the objective function, and then you differentiate. But in this differentiation, P is any vector, so you do not differentiate it with respect to rho. And after differentiation, you simply replace P by P rho. And actually, because you replace P by P rho, this partial derivative of L with respect to U vanishes, and you get the result. And you don't need a formula for the derivative of the solution of the state equation with respect to rho, because it vanishes thanks to the adjoint. Okay, so that's something that should be familiar to any expert in structural optimization. And actually, it's exactly the same that we are going to do for shape derivative. Okay, so the method of CA for shape optimization is simply applying this Lagrangian setting in the context of shape differentiation. So we build a Lagrangian that depends on the shape omega. It's not rho in this case, the density is the shape omega. You have U, the state solution, and P, the adjoint solution. And the definition of the Lagrangian, it is the sum of the objective function. And then what is the constraint? Well, that's the variable formulation of your PDE. Okay, I'm going to explain it in some details in a few slides. But then, as in the standard case, the definition of the by definition, sorry, of the Lagrangian, when you differentiate the Lagrangian with respect to P, you get the variable formulation for U. And then by definition, if you differentiate the Lagrangian with respect to U, you get the variable formulation of the adjoint. And then you have the theorem saying that if you take the partial derivative of the Lagrangian with respect to the shape omega, so you know the classical notion of shape derivative, then you get the derivative of the objective function. So that's exactly the same formula as if rho as if you were using a density variable rho. That's exactly the same process. Um, Let me give you three examples. I will take some time on the first example, and then the two other examples I will leave them and not discuss them. But you can, if you want details, you can just read the slide after the webinar. So the simplest case is the case when we have a Neumann boundary condition, and I'm looking at the equation minus Laplacian u plus u equal f. I just add a zero order term so that there is no compatibility condition on the source term f because I have the Neumann condition here. And then the variable formulation in this case is very simple. This is simply the integral over omega of nabla u dot nabla p. P here is like a test function, if you want, plus up minus fp, and there is no boundary term because of the Neumann boundary condition. And so that's my Lagrangian, depending on omega, depending on u, and depending on p. All right. And then what is really important here is, and that's why I did the case of Neumann boundary condition first, is that u, p, and omega must be three independent variables. And actually, u and p do not depend on omega because they do not satisfy any special condition on the boundary. Because remember, when I define the Lagrangian, u is any function in H1, p is any function in H1. They are not, for the moment, neither the solution of the state equation here or the solution of the adjoint equation. They are just any function in H1 of omega or in H1 of RD more generally. Good. So as I told you, by definition, dl over dp gives you the variable formulation of the state equation. By definition, dl over du give you the variable formulation of the adjoint equation. And if you do the computation, that's very simple. You get what you expect, simply the same type of PDE, but with a dummy load, which is minus j prime of u, where j is the integrand of your objective function, and the same type of Neumann boundary condition. And then the theorem is like in the standard method that the partial derivative of the Lagrangian with respect to omega is precisely the derivative of the objective function. And differentiating the Lagrangian with respect to the shape is simply because, of course, you do it, this is a partial derivative with u and p fixed. It's like differentiating an integral over omega of a fixed function. Okay, so the formula which is here is exactly the formula that we discussed in the first webinar when you were differentiating a fixed function integrated over omega. So this formula here is like the first example that we discussed in the first webinar. Okay, so it's very simple if you admit this theorem, and I'm not going to reproduce the proof. The proof is exactly like in the standard adjoint method. But if you admit the theorem, this proof is very easy. Okay, so we should not be afraid of computing shape derivative. This is standard if you follow the adjoint method, which in the case of geometric optimization is called the method of Sea. Good. I'm skipping this detail. Now let's discuss very briefly the second case of Dirichlet boundary condition. Here there is a subtlety because the solution u should vanish on the boundary, and then in the variable formulation, in the standard variable formulation, any test function u should also vanish on the boundary. And so that means that the variables are not independent, and then the method, the standard adjoint method, does not work properly. And so actually you should introduce another Lagrange multiplier to enforce the boundary condition. So that's a subtlety, and I'm not discussing the details in the case of Dirichlet method. Another case which is a little bit delicate is when you do a two-phase shape optimization, and actually you are not optimizing the boundary of the shape, but you are optimizing the interface, let's say, between the yellow and the red phase. And why is it difficult? Because the solution U is not smooth at the interface. Actually, you know that the standard transmission condition at the interface is that, of course, U should be continuous at the interface between the yellow and the red phase, but now it's a normal flux, which is continuous. So it's not the gradient, the normal gradient, which is continuous, because you have the two different material property, beta and alpha in the yellow and red phase. So that means that nabla u, at least its normal component, is not continuous. So you should be a bit careful when you define the Lagrangian. And again, I skip the details, but there are some difficulties in this case. All right. I think that's all I have to say about shape derivative. And now I leave the floor to Charles to discuss the second point.
Okay, so as Grégoire hinted at, I'm indeed going to discuss a few features that go a little bit beyond the standard, let's say, practice of the level set method and that allow to enhance its efficiency. The first one of these is what is commonly referred to as a Hilbert trick. So it starts from the realization that actually, what have we done when we search for the velocity that allows to update the shape from one iteration of the optimization process to the other? So we look at the standard structure of the shape derivative, which is this one. Okay, the shape derivative is the integral over the boundary of the shape of some scalar fields multiplied by the normal component of the deformation theta. And we say, hey, if I take theta is minus this scalar field v omega in the direction of the normal vector, then this gives a descent direction in the sense that the shape derivative becomes negative. So this gives a lazy way, in some sense, to find a descent direction for our objective function j omega. But this choice may be awkward for a series of reasons. And at first, one reason is that it only makes sense, strictly speaking, on the boundary of the shape omega and not everywhere. And remember that, for instance, in the practice of the level set methods, we need the velocity field to be defined everywhere on the computational domain, or at least in a band around the shape to be moved. Also, this formula may yield a very irregular descent direction, a very irregular vector field that causes numerical instabilities in the optimization process. So here is a very famous example obtained by Pironneau in the context of fluid mechanics, where he was optimizing the profile of the wing of an aircraft, and within one iteration, just because of numerical errors, the shape gradient was so polluted by numerical artifacts that this produced this very silly shape here with the bump, which is completely due to numerical artifacts. So there is a need somehow to smooth this shape gradient, at least to get rid of numerical artifacts. And there is actually a very elegant way, a very principled way to do both, to achieve both features at the same time, meaning to extend the velocity, the descent direction throughout a computational domain, and also to regularize it. And this is part of the shape optimization folklore, so it's a little bit everywhere in the literature. It's not easily found properly written somehow, and it's actually a common ingredient in the practice of gradient flows. So for instance, there is a very nice book of Neuberger that's about Sobolev gradients that you can find in the bibliography at the end of the slides. So what's the idea? To get into the idea, let me first remind you very briefly some basic mathematical definitions. So usually we consider Fréchet derivatives or usual derivatives, meaning that when we have a norm vector space or a Banach space and a function f taking values into R defined in this Banach space, the derivative is a linear mapping. Okay, it's a linear mapping that ensures that f at some point u perturbed by a very small vector v is at zeroth order f of u, and at first order something which is given by this linear mapping. All right. And so from this, we can infer another definition, that of a gradient. The gradient arises only in the Hilbert space context. So we assume that now the vector space x, which was here, contains a Hilbert space endowed with a scalar product, which is denoted with brackets here. And so the Riesz representation theorem shows that we have the existence of an element in this vector, in this Hilbert space H, such that f prime of u, the derivative at u evaluated in the direction v, equals some element in the Hilbert space against the direction v. Okay, and this is this element that is called the gradient. The interpretation of this is that if f is differentiable, then we have we have a gradient. F at some point u minus a small step tau in the direction u hat here. It's f of u as your order minus this quantity at the next order. And the Cauchy-Schwarz inequality shows that this is always larger than this quantity. And the equality only holds if and only if the direction is actually exactly the direction of the gradient. This says that minus the gradient of f is the best descent direction from f, starting from a point u. Okay, so this is pretty standard definitions, but they are going to be useful in a minute. So now let's return to our problem of finding a descent direction for our objective functional and look at what we have done. We have looked at this formula for the shape derivative, and actually I can rewrite this v omega, integral of v omega multiplied by the normal component of theta n as the L2 of the boundary inner product of v omega multiplied by theta dot n. And actually, what we have done is that we have chosen for j omega, to descend from j omega, the L2 gradient of the associated to the shape derivative j prime of omega. Okay, but actually, the thing is that we could trade this L2 inner product, which is an inner product of our quite irregular functions. L2 functions are not very regular, for any other inner product on a Hilbert subspace of C1 of RD, which is here. For instance, if we take any Hilbert space equipped with the inner product A, which is like this, we could search for the scalar field J, which belongs to the space H, such that for all test function W in H, A of J and W is J prime of omega, the shape derivative, in the direction of W, the test function, in the normal direction. And then the theory guarantees that the vector field minus J, so the scalar field J, in the direction of the normal is a descent direction for J omega, because A of Jj, which is J prime of omega Jn, is always positive by construction just because of this. Okay, so this guarantees that for any choice of the Hilbert space H, for any choice of the inner product here, moving a little bit omega in the direction of Jn in the negative sense is going to give a first order expansion which is less than J omega. So taking any J like this, not only that associated to the L2 inner product, is going to give some descent direction for the functional J omega, but naturally enjoys the features of the Hilbert space H. For instance, if H is a Hilbert space of functions defined everywhere on the computational domain, then J will naturally be defined on the computational domain. And if H is a Hilbert space of smooth functions, then J will naturally be smooth. So in practice, what do we do? The usual practice is to take H to be H1 of the computational domain, and though with this inner product, which is written here. So this is the L2 inner product of D, plus a small weight, alpha squared, multiplied by the norm, the L2 inner product of the gradients. And so the problem of finding here, this problem here of finding the H1 gradient associated to the shape derivative, it writes like this. We search for any function W in H1 of D, the function J, such that this equality is satisfied. This is just a finite element problem for a Laplace-like equation, okay? So this is very, very cheap to solve. And because if we solve this, then J here will be a regularized H1 gradient for the shape derivative, okay? Actually, what is this alpha squared, which is here? Then the solution to this guy, to this problem here, we can write it as an integral over here, where J is a fundamental solution. This is a convolution. So forget about the formula, but this is a convolution. And the radius of the convolution is alpha. Think that the larger alpha, the larger the radius of the convolution, which is here, and the larger the radius over which we are going to smooth the information contained in the shape derivative. Okay? So this gives a principled way to infer a gradient which has good properties for the sake of optimization. So in practice, we take alpha to be a small number of mesh size, meaning that we are going to average, in some sense, the information of the shape derivative over a small number of mesh size. This idea is formal in the sense that H1 of D is not a subset of C1 functions, but in practice, it turns out to work pretty well. Okay. So actually, we can consider other regularizing problems over vector functions, for instance. But I'm going to skip this part. It's also a matter to infer descent direction from the volume form of the shape derivative. So it's a little bit technical here, but you can find nice information in this article here, which is referred to at the end of the slides. And most importantly, this Hilbertian structure over the space, over the set of admissible directions, deformation directions for the shape, paves the way to constrained optimization algorithms to be carried out in the context of the level set methods. So let me now discuss about this jump to the part where we can employ this idea to deal with constraint optimization in the context of the level set method for shape optimization. So remember that for now we have only considered constraints, very, very simple constraints that were taken into account by a fixed penalization of the objective function by the constraint function. We are solving minimization of the compliance plus a fixed weight multiplied by the volume of the shape, for instance. Now we wish to solve constraint optimization problems of this form. So let me frame the problem in the setting of the Hilbert spaces, since we have seen that we could consider that deformations of a given shape can be given a Hilbertian structure thanks to this nice Hilbertian trick that I have referred to just before. So we consider an optimization problem like this, which is set in a Hilbert space capital H. Here the design variable H belongs to this Hilbert space capital H, which is endowed with a inner product A, which is written here. And we minimize an objective function under a collection of equality constraints. We could also consider inequality constraints in pretty much the same spirit. So there are a variety of optimization algorithms to solve such problems, for instance, the augmented Lagrangian methods, sequential linear programming, etc., etc. And here I'm going to emphasize on a quite new algorithm that works pretty well in practice, especially for the purpose of shape-n topology optimization. This is called the null space algorithm, and it is based on a linearization of this type of problem. Okay. So what's the idea? The idea is that the resolution of this problem, it proceeds by iterations of this form. We have a series of iterations, and each new shape Hn plus 1 is obtained from Hn by an update of this form. This update is made of two steps. One is called the null space step, the xij, which is here, and the other one is called the round space xij, which is here. Okay, and both are weighted by fixed weights alpha g and alpha j. All right, and there is also a small pseudo-time step, which is tau and which is here. Okay, so we place ourselves at a given iteration of the process, and we denote by theta j and theta gi's the gradients of j of h and the constraints gi, which are here. So let me remember that they are obtained from the Riesz representation theorem by these formulas from the derivatives of j of h and gi of h, which are here. Okay? And we search for both directions, so the null space direction and the round space direction, by definition, they are orthogonal. Okay? There are combinations of theta j and theta gi, which are written under this form, and we are going to search them under this form in such a way that they fulfill a certain number of desirable properties that I'm going to discuss now. So psi j and psi g, they are orthogonal, like is written here. Okay? The first direction, the null space direction, it's going to be an orthogonal projection of the gradient on the null space of constraints, meaning that it is a direction, psi j is a direction that aims to improve the value of the objective function, to decrease the value of j of h, while leaving the constraints untouched. It doesn't change the values of the constraints at first order. Okay? So for us, it's going to be the projection of the gradient of j on the null space of the constraints, on the space which is orthogonal to the gradients of the functional GIs. Okay? It is the best descent direction for GH that leaves the constraints untouched at first order. So we use, it is defined by this property here, but that is very simple property in Hilbert spaces, okay? And in matrix form, this rewrites like this thing here, with a matrix S, which is a matrix with the size of the number of constraints, okay, which is given by Sij, the element ij is A, the inner product of my Hilbert space, theta gi and theta gj, which is here. And this matrix can be proved to be invertible, provided the gradients of the constraint satisfies a simple, let's say, constraint qualification condition. And B here is the vector field obtained by assembling this thing, which are here. Okay, so it's completely explicit right inside. So we can calculate this vector just from the look of the gradients of J and GIs. The other direction, the round space direction, it's a direction which is orthogonal to the null space of constraints. It's only done to reduce the violation of the constraints. So by definition, we are going to search for this field psi j, which is here, so that one small step tau in the direction here against the range space step aims to reduce the constraints, reduce the violation of the constraints by a rate alpha j. So we impose this relation to hold. Using a first order expansion, this rewrites exactly like this. J prime of h in the direction psi j should be equal to j of h. And putting this into coordinates, meaning writing the expansion of psi j over the gradients of the constraints, this rewrites as a linear system of this form, okay, with again the same matrix S as before, and another right-hand side that can also be calculated completely explicitly. So we have recipes, formulas for calculating this null space and range space directions explicitly. Then we can use a merit function, which is a function that should be minimized by our update. Our update is made of the null space step here and the range space step here, weighted by these two factors here that weigh the respective importance of decreasing the objective function and reducing the violation of the constraints. And the merit function is a function that should be minimized by this update set. This is done to assess whether we have done the time step. The time step that we have used is too large, or if it is suitably small. So the gradient of this merit function is by construction the minus the update step. Okay. So one good side of this strategy is that it's almost parameter free. There are only two parameters in this strategy, which are the weights alpha j and alpha g, at which we want the algorithm to decrease the value of the objective, and we want to reduce the violation of the constraints. So there are only really two parameters. It's a very sensitive algorithm to work with, sensible algorithm to work with, sorry. And with minor adaptations, it can be adapted to shape optimization because, as we have seen, shape optimization can be given somehow with a Hilbertian structure by the Hilbertian trick that I have mentioned just before. So let's consider an example. We consider the minimization, the optimization of a bridge. So this is a 2D bridge, which is clamped on the bottom parts here, and we apply loads on the upper deck, which is here. We minimize the volume of the bridge, okay? And we put 9 constraints. Each constraint is associated to the compliance of the bridge when it's submitted to one of the load cases. Okay, so we have a constraint for the load G1 here, a compliance constraint for the load G2, etc., etc. Okay, and we solve this problem with 9 constraints with the help of the null space algorithm. So this is what we obtain when we have only one load, meaning we only consider one constraint with the compliance with the load centered at the middle of the upper deck. This is the shape that we obtain for when considering free load constraints, and these are the optimized shape of the bridge when considering the 9 loads constraints, the 9 constraints and 9 compliances in the 9 load cases. All right. And so just a word of advertising to say that this optimization algorithm has been given an open source implementation thanks to our colleague Florian Fapon. So feel free to go to this GitLab page and to download this plot. So this is a very nice Python package that you can use for your developments.
Charles, I think there is only 10 minutes left, so...
Yes, I'm almost done with these parts. Thank you, Grégoire. Okay, so I'm going to skip this third part, which is devoted to the practice of the level set method on triangular meshes. But I just would like to mention that the solution of the level set Hamilton-Jacobi equation and the calculation of sign distance function can be done exactly with the same efficiency as Grégoire presented last time in the realm of Cartesian grids in the case of triangular meshes. So this is in the slides. And here is a link to some libraries that allow to do that are open source also. And just a last word to mention that there is one drawback that we have mentioned last time about the practice of the level set method for now is its inability to create holes inside the structure. Meaning that for now, the level set method can accommodate certain topological changes. For instance, opposite walls can merge, for instance, holes can merge, but you cannot nucleate holes inside the bulk shape. And there is actually another complementary means to calculate sensitivity of functional that allows to do that. This is what is called topological derivatives. So topological derivatives, they evaluate an expansion of the objective functional with respect to the nucleation of a small hole. We make perturbations of a shape omega of the form omega x epsilon, where we remove a small ball from omega. Okay, and so if this topological derivative that appears as the first non-trivial term in the asymptotic expansion of j omega x epsilon is negative, this means that it's beneficial to drill a small hole around x. So we can calculate topological derivatives. So here is a formula for the topological derivative, the compliance in the elasticity context. And we can actually incorporate this into the shape optimization framework that Grégoire recalled at the beginning of the lecture. At every several iterations, we can just not do the Hadamard shape derivative process to just move the boundary of the shape, but instead we can calculate topological derivatives, inspect where it is minimum inside the shape, and insert a small hole inside the shape where it is to try to decrease the functional by insertion of a hole. So here is an example with the optimization of the bridge. We consider the classical bridge shape optimization example, where it's just clamped here and here, and we apply the load here. We minimize its compliance under volume constraints. And we start with a very, very simple initialization, which is this one. And by using this combination of the shape derivatives and topological derivatives, we finally obtain a shape which is plenty of holes that couldn't be obtained just by moving the boundary of the shape. And so the floor is yours, Grégoire.
A few comments about related techniques. But before that, we forgot to include a slide on the history of the level set method in structural optimization. And I have to say that the first paper in this topic was a paper by Sitian and Wigman, where they used a complicated immerse interface method, which actually is very nice, but maybe too much compared to the ersatz material method. And also, one defect of this first paper was that they were not using shape derivative, but some heuristic criterion based on the von Mises criteria. Then a second paper just after was by Osher and Santosa. This was rather an interface optimization for a two-phase scalar problem, and they use indeed a shape derivative. And then 1 year later, I produced with my colleagues François Jouvre and Anka Maria Toader one version, and then at the same time, Michael Wang in Hong Kong and his collaborators also did a contribution in this setting. And then after that, so many contributions that it's not possible to list all of them. Good. Let me make maybe one recommendation, which is we prefer to use Hadamard shape derivative, which are really adapted to a clear, crystal clear interface. But there are some other author which are instead using the level set function itself as the optimization variable, right? And so what do? They introduce a regularized heaviside function with a small parameter epsilon, for example, this one. And so with this definition, they introduce a regularization of the characteristic function of the domain defined by phi. And then they said, well, I have coefficient in my PDE that depends on phi, and let me do the optimization with respect to phi. So they use phi as the optimization variable, a little bit like a density variable, and they do not use the notion of Hadamard shape derivative. This is a little bit dangerous because you have intermediate values between 0 and 1, which may be favored by the optimization. And actually, because you introduce some kind of composite material for the values between 0 and 1, which may be beneficial, but they are not physical. And so you need to redistance or to recompute phi as a distance function very frequently, because that's a matter of penalization in some sense. And you know that in the SIMP method, the most tricky part is the penalization when you want to remove intermediate density. So if you use this instead of the Hadamard shape method, there is a danger that you favor too much intermediate density. Of course, there are other methods which may be related to the classical level set optimization. And one which is very popular is the so-called phase field method, which is kind of similar in some sense, because you also have a function phi that takes value between 0 and 1. When it is 0, that's a pure phase alpha. When it is 1, that's a pure phase beta. But for intermediate values, you have some kind of mixed composite material, but you penalize the value of phi to be close to 0 and 1 by introducing an approximation of the perimeter, which is a kind of a penalization with a double well potential here, with a 1 over epsilon. So you really force phi to be close to 0 and 1. But the fact that you add this term means that you are approximating the perimeter of the interface that separates the two regions between the two phases, corresponding to phi equal to 0 and phi equal to 1. And then you add simply this penalization term to the objective function, and you perform optimization with respect to phi. Good. There is also a variant of the level set function, which was proposed by Samuel Amsust and his collaborator, which is to use a topological gradient and then to define a different type of a level set function, which is based on this topological gradient, right? And actually, you write the first order necessary condition corresponding to this notion of topological derivative. So this is, omega is going to be optimal if this term is always positive. So you ask that this term is positive inside omega, and because you can also compute this topological derivative outside from omega, you ask it to be negative outside from omega, right? And then what you do is that you are trying to find a level set function that you normalize to be of L2 norm equal to 1, which is proportional to g of omega, and you want it to be strictly negative inside omega. Okay, so you want the optimality condition for the topological derivative and not for the shape derivative to be satisfied. So he has proposed a level set algorithm, which is kind of different because there is no advection. It's more a fixed point. So you update, the level set function in terms of the shape derivative, which is given by this gn. So it's a different kind of an algorithm based on a different kind of shape derivative. And here is just a very the movie does not work at my place. Sorry, that's just there was a movie on the slide. Sorry, to explain how it works. Good. Then another possibility is to replace the advection of the level set function by a kind of a reaction diffusion equation for phi. So this was proposed by some author, I guess, that do not like a convection term, if they use finite element software, which is not adapted to a convection term. And so if you instead use a reaction diffusion term where the reaction term is nonlinear, you may have a kind of an advection term that appears in the limit. And then they also rather use a topological gradient, but sometimes they use the shape gradient. But okay, that's a kind of a variant of the level set approximation. And I leave the floor now to Charles to conclude.
Okay, thank you, Grégoire. So in a very, very short time, I will present two numerical examples that make use of some advanced concept, advanced use of the level set methods. So the first one of them arises in the context of nanophotonics. So we consider the optimization of nanophotonics, which are small devices, which are components of photonic integrated circuits that conduct light, considered as a wave. So in such circuits, the light is transported by waveguides.
Charles, you should share your screen, I guess.
Is it not shared?
I don't see it.
I see it.
Oh, you see it? Okay, sorry, that's my fault. Sorry.
It's okay. Okay.
Maybe, yeah, I see it also on YouTube, so it's fine.
Is it okay?
Yep.
Okay. And so the light passes through waveguides, which are here, and this waveguide. So the light is described by electric and magnetic fields that are the solution to the time harmonic Maxwell equations. And so the shape we inside between these waveguides, we put small nanophotonic components to do some effects to act on the light on the input wave and to produce some effects as regard the output waves. So to achieve this, we play with the inclusion of air inside the silicon that is the constituent material of the nanophotonic components. So here is optimization of one first nanophotonic component called a duplexer. So we have one input waveguide at the entrance, two input waveguides at the output. And inside the input waveguide, we have two waves that can pass. One is blue, the other one is red. And we want that the blue wave be completely routed in the upper part and the upper output waveguide, and the red wave be guided completely on the lower waveguide. So this is a 3D computation on the whole impedance, but we only see the shape in 2D from above. So the optimization takes place in 2D, but the physics takes place in 3D with the guides that are in silicon, the matrix, the substrate is in silica, and there is a PML outside to describe, to account for the effect of that the waves go to infinity. So we start with a very, very simple shape here for the duplexer, and here's what we obtain. We see that on the bottom part, it's the energy of the wave when it is red. On the upper part is the energy of the wave when it is blue, and we see that we playing on the shape of this inclusion, we are able to route the light in the desired output waveguide. Here are also some other examples of optimization of other nanophotonic devices. So here is a power divider that we divide the power injected into the input waveguide into two output waveguides equally. So this is the shape of this device. This is a mode converter where we convert the first tier mode in the input waveguide to the third tier mode on the output waveguide, which is here. And here is a polarization converter where we transfer the first transverse electric mode to the first transverse magnetic mode, which is here. Another example of application of these advanced concepts arises in the context of additive manufacturing. So this was from a study made by Grégoire, Martin Beer, Benny Bogosel, and Mathias Godoy with the company Safrantech. And so it arises in the context of additive manufacturing, which proceeds by slicing the shape to be produced in a collection of 2D layers and by constructing these layers one on top of the other. And as you know, there is a terrible thing about that overhang patterns, like very large horizontal regions like that hanging over void, are difficult to assemble for a number of reasons. To alleviate this issue, we erect a support structure S alongside the shape, but this support structure is to be removed at the end before the final use of the shape omega. So here, let's consider the optimization of a 3D bridge and of its support structure at the same time. So the objective function is of this form. It's the form of the compliance of the shape in its final use, plus the compliance of the shape and the supports, so the total structure in the context of their construction. So here is what we obtain. This is the shape, the optimized shape, and this is in blue, the optimized support structure for this shape. But the bad thing is that this support structure has to be removed after production. And here, all the parts of the support structure are not necessarily accessible, depending on where we want to access the support structure to remove it. For instance, if we want to access the support structure from both sides here in green here, all the structure here is not accessible, and we are not going to be able to remove it. So to do that, we had an accessibility constraint of the shape that I'm not going to discuss here. It would take like a whole presentation to do this. And this one, just let's mention that this one is based, it's modeled from the sign distance function to the shape. And here is what we obtain after imposition on top of this accessibility constraint for the support structure. So now we see that the structure is fully accessible, meaning the accessibility constraint is violated here in a lot of regions if we do not impose this accessibility constraint, and in very, very small regions when we impose these accessibility constraints. So before closing this second session, let me say one word about the general assets of the methods. So the asset method is globally relatively cheap, meaning that all the computational expense is put on the numerical solver, on the finite element solver, the solution of the Hamilton-Jacobi equation, the solution of the fast matching method are very, very cheap. And one very nice feature is that the variable is a shape, meaning that we can express the mechanical constraints and the geometric constraints such as thickness, overhang, accessibility, etc., directly in mathematical terms without any reformulation, for instance, as opposed to density method where sometimes you have to interpret some constraint or some feature in terms of densities, while they would be more naturally expressed in terms of shapes. There are certainly some drawbacks, but still you have a fixed mesh method, and so you need some approximations of the physical equations. So this is an earth material approximation when you are in the realm of linear elasticity, but in more intricate physical context, this could become much more challenging for the numerical accuracy of the finite element resolution. And also, we have made all the computations at the continuous level. We use shape derivatives at the continuous level that then we discretize, which means that we have some kind of inadequacy between what we optimize and what we calculate. This may cause endanger a bit the convergence of the method, which is never perfect. And with that, thank you very much again for your attention, and hope to see you for the third webinar next week.
Thank you so much, Grégoire and Charles. This was very good. So, audience, if you have any questions, please go to the bottom. You will see the small button with the Q&A. You can type in your questions. So we had some questions during the talk that have been answered by text. So if you didn't notice and you asked a question, please, you can also see them under the Q&A. You can see the answered questions. So maybe we take these live that are coming in now. So there's one question about the nanophotonic devices, and the question is whether the optimization was performed for a single operating wavelength.
Okay, so that's a good point. So the results that I have shown here. So here you are in the optimization of this device here. You have two wavelengths because you want the power to be maximum in the upper channel when considering the red wavelength, for instance, and to be maximum when you in the lower channel when you consider the other wavelengths. But I think that your question is about robustness, meaning are these shapes robust if we do a small perturbation of the input wavelength, for instance, if we have some uncertainty about the input wavelengths. So the shape that I have presented here, they have been done without considering robustness, possible uncertainties on the input wavelength. But in the study that these examples are based, there are some examples where we enforced robustness with respect to the incoming wavelengths, for instance, with first order derivative methods. I could elaborate more on that if you're interested. But these examples here are not robust to the wavelength, but there are some other examples that we did with the same study that were.
Okay, thank you. So while more questions potentially come in, so I have a question. So, as someone coming from density methods side of things, I have always heard and maybe still feel that shape gradients are difficult. Of course, you also have to get used to the approach of doing the analytical adjoints for density methods. But I have the question that now, for at least for density-based methods and stuff, we can really exploit these automatic differentiation tools that are available in various packages. Does something similar exist for shape gradients? Like, can you automatically derive these gradients without having to do all the hard work?
Very good question, Joey. Thank you for asking it. So I must admit that if you are not accustomed to shape derivative, it's a bit tricky, and I will try to make it as simple as possible, but it's sometimes a little bit delicate. Well, the adjoints are the same. There is no difference in the notion of adjoints. But now the question of automatic differentiation, I was not convinced at all, but I discovered the work of Peter Gangel. So I can give references if somebody is interested, who use shape derivative, but the volumic form of shape derivative. In the slide, we insisted on the surface force, which has a nice interpretation saying you should deform your shape like this. But by integration by part, you can write the shape derivative as volumic force, and then it turns out that they have all the same structure, and it is amenable to automatic shape differentiation. What do I mean
Okay.
by automatic? If, for example, you use a software, Peter Gangel did it with ngSolve, which is a software like Phoenix, like FreeFM, where you have a language in which you write variational formulation, and then you can indeed do compute the adjoint and the derivative in the volumic force, in the volume form of the shape derivative by automatic differentiation. That's very clever. I must admit that I discovered this a couple of years ago, and I think it's a very nice idea. So it's not completely general because it works for some type of problem, but if you come with a new problem, let's say with three different materials, I would say, it's a bit more complicated, but it's doable, yes.
Okay. Yeah. That's good to know. Yeah, because that is something that at least I see the students can get quite far with not having to deal with all the hard
Yes, I
work that
understand.
we are used to doing. Okay, that's very nice. So we have a question again about the photonic problem. So the question is it only shape optimization or also topological derivative based optimization?
So here we only use shape optimization based on the shape derivative. You could certainly use topological derivatives. I think there is an article by Samuel Hemstutz that computes topological derivatives in the context of the Maxwell's equation. But I'm sure that the results exist in the literature. Here we only use shape derivatives and using initial shapes that have a lot of very, very small holes, like I have presented here.
Yeah. I have another question in the meantime. So you say that you use the shape as your variables, right? Your design variables, basically. Can you repeat again how you do that in terms of the null space optimizer? So what are the sort of input and output variables of that one?
Mhm. So do you, do
Charles, I
you
mean, because you explained it.
okay. Okay. So let me come back to this. So at some point, let's say that at some iteration here, you have calculated the shape derivative of the objective function and the same for the constraint functions. Okay. Then with the Hilbertian method, you calculate H1 gradient for the objective function and also for the constraint functions. So that's functions, the gradients of G and the gradients of the GIs, they live on the fixed computational domain D. Okay? And then you are completely in line with this. There's functions that belong to a Hilbert space, which is H1 of the fixed computational box. And you can apply the null space algorithm exactly as is in the black box. For instance, the example that was done here, it's really an example where you just feed the gradients as a finite element function, and then it cooks. If you have some routine that calculates the gradients and some routine that calculates the inner product between two gradients, then the null space optimization algorithm computes automatically the coefficients and the weights that produce the descent direction. So this is something that you could completely use this algorithm in the package that I mentioned in the black box fashion.
Let me
So
add,
yeah,
let me add before you say a word, Joey, sorry,
that's
that
okay.
if you have another favorite algorithm, let's say if you want to use MMA, for example, you could,
Yes.
Yeah.
But of course, why we are not using MMA is that MMA is really very well adapted for density method. But the upper and lower bound for displacing a level set function does not make much sense. So it's not very efficient, I guess, MMA in this particular setting. But if you
Yes.
want to use it, you can.
You could use also exactly in the same fashion sequential linear programming
Yes,
or
it was done by
Yeah.
Alicia Kim.
Alicia Kim
Yeah.
and Peter Dunning, yes. And the
So
fact is
do I.
that
Yeah.
we felt that this one is good. We like this one because it doesn't have like parameters that you have to tune somehow without any physical taste of what they mean. Here
Yeah.
you have two parameters that are quite physical, and there is really no other parameter that you have to fine tune
Yeah.
to use it.
But do I understand correctly that the sort of design variables that you're updating are still the level set function in some sense, but you're using the shape gradients in a
Yes,
volumetric sense somehow?
yes,
Yeah, okay.
yes.
Okay, now I get it. Okay, I don't think there are any more questions, so we made it through. And let me just, at the end
Oh,
here,
I'm
I will
going to end
just,
soon.
yes, this one. So just make the advertisement for the last webinar. So it will be next Thursday, so the 28th of May, same time, same place. And I hope to see as many of you there as possible. And thank you for coming.
Thank you.
Thank you very much.
Yeah, and thank you, Charles and Grégoire. Thank
Thank
you
you.
very much.
Thank you very much.
Bye-bye.
Bye-bye.
Bye.